All right, so here you guys are beginning our new unit. It's unit 4, and we'll be looking at kinetics and equilibrium and reaction rates. The lesson that you guys have for today is looking at what reaction rates are and some of the factors that we know that would actually affect your reaction rates. And it looks like my screen definitely has a little bit of a lag here, so you guys might see me kind of trying to move this around as we go through, but I'm just going to walk through the first page of the notes that you guys have with you guys so you could do the homework for tonight, which is the very first homework assignment on the unit calendar that you picked up today. And we have some definitions that we'll be looking at. The first definition that we have right here is this definition of a spontaneous reaction, and the key word here is the word spontaneous. So these are reactions that would normally happen, so that will eventually happen. We just don't know how long it's going to take. Some spontaneous reactions might take a second, and some might take several years to happen. So these are reactions that would typically happen. It's just we don't know how long it would take. Okay. So we know that a diamond, if given enough time, thousands upon thousands upon thousands of years, it will eventually turn to another form of carbon, which is graphite. And we would call that a spontaneous reaction because nothing really needs to be done for this to happen. It just will happen eventually over time. Okay. And in this unit, you guys are going to be studying what a reaction mechanism is. And these are the steps by which a reaction will take place. Okay. So we also know that there are different factors that could affect how fast a reaction goes. And if you think about a rate, an easy rate to remember would be the speed of a car, right? You're looking at how much distance something travels in a given amount of time. When we talk about rates and reactions, we're basically looking at the concentration of something, reactant or product, given a set amount of time. So whenever we talk about a rate, we're talking about how fast a reaction or how slow a reaction is going. But when we say how fast or slow, we're really looking at the concentration of things disappearing or the concentrations of things getting made versus time. So time is always an important element when we're considering out rate. So for a actual chemical reaction to occur, you know that two molecules need to go through a collision. And you guys should remember talking about collisions from last year. You know that if you have two molecules and they are going to be hitting each other, okay, if there's enough energy between the collision, we could get bonds being broken and new bonds being created. And there's different ways to actually help these collisions occur. I'll put up a link to a little cute YouTube video about reaction rates and different things that could help collisions. If you had me last year for chemistry, you probably remember watching it, but I'll put the link up to that along with your assignment today. So in order for collisions to happen and for the collisions to actually cause a chemical reaction, your collisions need to have a sufficient amount of energy. And this should make sense for you guys. If you have two molecules that are hitting each other, but they're going at a very, very, very slow speed, and there's not a lot of energy involved, then basically the molecules are just going to be able to bounce back off of each other, and they're not going to have new bonds that are being broken or new bonds that are being created here. So another way to talk about this energy that we need for a reaction to occur is the word activation energy. So we're going to add that in over to the side. And this would be a good word to have highlighted in your notes because it is a vocab term here. Okay, so your activation energy is pretty much just the energy that you need from two molecules colliding in order to create an actual chemical reaction here. And another thing that you guys need to know is that the molecules, they could hit at different kinds of angles. Like you could have maybe one molecule facing forward and another molecule in a different direction, and they could hit. But in order for the reaction to actually take place, we say that the orbitals, and the orbitals are the places where you have your electrons. And remember, electrons are the things that are involved in creating bonds. The orbitals have to be correctly aligned, properly aligned for your chemical reaction to actually take place between the two molecules. Another way you could think about this too is if you have two cars, you know that you could have different amounts of collision energy depending on where the cars would be hitting each other in a car accident. So kind of the similar idea, the two molecules that are colliding have to be in a proper orientation to each other to actually get a reaction to occur. And we're going to also look at different ways to actually speed up a reaction, to increase the rate of a reaction. And these are some things that we talked about last year in honors chem and general chemistry, but one really easy way is to take a look at your concentration. And by increasing the concentration of stuff you have, increasing the number of molecules that you have in your solution or in the reaction that's going to occur, you would actually increase the number of collisions that take place. So you would increase the collision frequency. Okay? And the more collisions that happen, basically the greater the chance that you have for actually creating new products. And another way that you guys could increase the rate of a reaction is to take the temperature of something and increase it. And if you up your temperature, basically your frequency of collisions are going to go up again because you have molecules that are moving faster and the collisions also have a lot more energy to them. So let's go ahead and summarize that out. You're going to up your collision frequency because you're going to up your collision frequency because your molecules are moving faster. And thus, your collisions also have a lot more energy to them. Okay, so you could think of increasing temperature or something like if you took the speed of a car on a freeway and you actually increase the speed of it, right? You're going to have a much more greater likelihood for things hitting each other and also for collisions having a lot more energy when they do hit. So these are two big ways that you guys could increase the rate of a reaction. Another thing that you could do is you could change something about the actual physical state of the compound that you're working with. So we could do this by taking a solid, and if you ground that down to finer particles, you would actually increase the surface area. And again, if you increase the area, you have more likelihood for collisions to actually happen. So you would increase the rate of the reaction. So the main thing I want you guys to really remember about reaction rates and actually changing those reaction rates, it's all about the word collision. The more collisions that you have and the collisions that you have with greater energy, these are all much better ways to actually get a reaction to happen. And remember, we could do that by upping your concentration. So you have more molecules that are available for the collisions. You could increase your temperature, which would increase the number of collisions that happen just because you have things moving at a much faster pace. And not only that, the more energy would give you a much greater chance of overcoming this activation energy for the reaction to happen. And the third thing you could do is you could also mess with the physical state by grinding something down or by increasing the surface area of one of the reactants. You also would give a chance or give greater chances for the molecules to go through and collide with one another. And the second part that we're going to be looking at today is this little graph over here that you guys have in your notes. And the reaction here that you're looking at is actually dealing with hydrogen gas and iodine being created to make hydrogen iodide. And we'll look at this reaction together. Earlier, we talked about what a rate was. We said it was looking at the change of something over time, like speed is looking at the change of distance over time. But when we talk about reaction rates in chemistry, we're really looking at concentration and the change at the concentration you could have depending upon your time change. So one way that you could write that out is you could say it's the concentration of something. So the concentration of A at a point in time, we'll call it time 2, minus the concentration of A at your starting time, which is time 1. And then if you divided that by your change in time, so T2 minus T1, that's one way to pretty much define rate. So it's the change in concentration over the change in time here. And that could be summarized just by putting in something like this here. So you have the change in concentration of A divided by the change in time. And that's just a simpler way to write that out. So if you were to summarize out this equation again, it's just the change in concentration of something per your unit time. And remember, per just always means that you're looking at it divided by something else. So concentration over time is what we're looking at. And here you guys have a chemical reaction, the one that I just mentioned earlier that we're going to be looking at. So you have some iodine reacting with hydrogen, and the product of it is hydrogen iodide. And if you look here, the coefficients are telling you a lot about what's going on. So as you have iodine and hydrogen reacting 1 mole of each, you actually end up making 2 moles of hydrogen iodide. And you could see why. You could see that we're dealing with diatomic molecules here. So for I2 and then for H2. And then because of that, we get a coefficient of 2. So if you were to summarize this out by also looking at our little graph that we have over here, as the reaction happens, and remember from the very beginning, you're only starting off with the reactants, and then we are going to be creating products. So as the reaction progresses, the concentration of your hydrogen goes down, which makes sense for us because as the reaction happens, we're using up the hydrogen to make up our hydrogen iodide. And similar to this, as the reaction is going on, what else is going to decrease? It's going to be the concentration of iodine. So these two things, because they're getting used up as reactants, as time passes, we're going to be dropping the amount of the hydrogen and the iodine here. And what is actually going to be going up as these two guys go down, we're going to be creating more of the hydrogen iodide here. And let's also bring in the factor of the coefficient of 2 because that's pretty important for us. So as the reaction progresses, as hydrogen and iodine are going down, as the concentration is going down, the concentration of hydrogen iodide is conversely going to be increasing since we're using these two guys to make that guy right there. And here we're also going to bring in that we have a coefficient of 2 in the front, and we know that the concentration of hydrogen iodide is actually going up twice as fast. So for every iodine and for every hydrogen that's being reacted, we're making 2 hydrogen iodines. So we say that the concentration of HI goes up twice as fast here.